Okay, welcome everybody to today's data science seminar. We're very pleased to have our very own Alice Paul. Alice is an assistant professor in biostatistics, and she just started at Brown after having served as a faculty member at Olin College in Massachusetts. And then prior to that was actually postdoctoral fellow in the Data Science Initiative, working with Pedro Felsenswald, who's with us here, I see. And then prior to that, Alice got her PhD at Cornell in operations research. Is that right, Alice?
Yep, that's right.
So we're very pleased to have Alice here to give a talk, but also more importantly, probably we're very happy that Alice is now rejoined as a member of the Brown community. So welcome on two levels, Alice, and really looking forward to your talk. And so when you're wrapping up, I'll also moderate the Q&A.
Thanks, Joe.
Okay.
Yeah, so I'm really happy to sort of be giving this talk. It's joint work with my postdoc advisor, Pedro Felsenswald, in engineering/computer science here at Brown, and also with Caroline Clevens, who's in applied math at Brown. And so this was started when I was a postdoc, but sort of completed when I was at Olin, actually. So today I'm going to be talking about clustering and a particular way of sort of approaching clustering, and sort of all tied together to this general optimization idea of iterative linear optimization. So as I talked about before, this came from a project that I started when I was a postdoc. And it was a fun project to work on because it involves a couple of different areas. So as you can tell from our backgrounds, we have like engineering, computer science, data science, and applied math. And so that was the fun thing about working on this project, is that we have clustering sort of coming from data science. We have linear optimization, thinking about applied math. And then we also have semidefinite programming, sort of coming from like a theoretical computer science background. So the work has actually been sort of split up into two pieces. So these are the two papers that I've put links to here. And one sort of focuses on more of the optimization and thinking about it, this iterative linear optimization map that we can think about in multiple different contexts and analyzing how that map behaves. And the second piece is taking that map and applying it to clustering and semi-definite programming in particular. So there are two pieces, and I'm going to focus on the second piece today. So thinking about the actual applications to clustering and semi-definite programming rounding. But if you're interested, there's a lot more sort of beautiful math behind some of these ideas. And so if you're coming from a more applied math background, that first paper, I think, has a lot of really cool things with eigenvectors and curvature, etc. So I'm going to first give a little bit of background on clustering in general, and then I'm going to give a roadmap for the rest of the talk in relationship to how we will approach clustering. So when we think about clustering, it's one of these key problems that we see in unsupervised learning. And the idea is that we want to identify natural groups in unlabeled data. So if I think about the picture on the left, this is data where it has been generated by a mixture of Gaussians in 2 dimensions. And the colors represent like which Gaussian each point was generated from. So in that case, I would actually like be seeing the answer, and I'd be able to tell, yeah, those points look really close together. But I have that color that is sort of guiding also how I'm interpreting that picture. And really, when we're in the unsupervised learning case, we're not given that nice coloring there, right? We're in the right-hand side picture where we get some data, and the idea is that we want to discover these clusters. We want to discover these groups. And so we need to think about how are we going to do so in a way that if we then colored them, they then looked intuitive to us, if we were able to sort of visualize them. And this can come about from a couple of different contexts. One, we may just want to sort of be exploring our data and understanding any subpopulations or patterns that we can observe. So for example, you might discover or look for natural groups where you could see like patients naturally group into a couple of different clusters and they have different patterns in their symptoms. Or you could think about it in conjunction with like a predictive model, where then you use this information that you're learning from the clustering to then do some prediction. So either you're fitting a model within each group because you observe different behavior, or you're thinking about using this clustering output as a variable that gets fed into your predictive model. And when I talk about natural subgroups, and we think about that picture on the right, what is a natural subgroup? Well, there's many different ways that we can define what it means to look like a good cluster. So this picture is from Python's scikit-learn package or library in their like clustering page. And on the rows are different data sets, which are toy data sets. And on the columns are different algorithms that they have implemented and the results that you'd get from running that algorithm on that data. And so from looking at the picture here, you can sort of see that different algorithms are approaching the problem in a different way. They're looking for a different kind of underlying structure to the data. So we can have things that look for clusters that are very dense, so density-based clustering. We can also look at graphs and network structure to think about how we can find communities and clusters within a network. Or we can think about things that are sort of distance or similarity-based metrics. And most of these optimization problems, no matter how we're sort of defining them, these are NP-hard problems. We're trying to think about these discrete number of groups that we're looking for and to optimize whatever metric we've chosen. And so we generally are landing in this hard optimization problem world of NP-hard problems. And one of the most popular algorithm would be the k-means algorithm or variance thereof. So you have, for this particular kind of clustering, we can think about it as being based on distances. So for k-means, we want to find k clusters, which could be represented by the subsets of points that we assign to each cluster, each group, so that we minimize the distance of points to their center squared. So if you look at the first objective function here, this is like the mean, that center, that sort of representative point that could sort of summarize that cluster. And then we're minimizing, summing over all the points, the distance squared to their cluster center, which we could also have equivalently wrote by summing over all pairs of points and looking at their distance squared, but then we add in a weight by the size of the cluster. So these are equivalent ways of representing this optimization problem. So this is a way of sort of capturing those spherical clusters where we are looking for clusters where things that are a small distance are put into the same cluster and things that have a larger distance are put into different clusters. And so that leads to the idea of like a good clustering, looking at the reduction in this sum of square distances. So you've sort of reduced the total amount of sum of square distances by only looking at the points that are put together in this right-hand side objective function. And so by doing that, you've sort of taken out these larger distances that were between points that you've now assigned to different clusters. So that's one sort of popular algorithm. It has some downsides to it, and the algorithms that are used to approach this are heuristic algorithms. So they do not have a guarantee on how good that solution is going to be with respect to that objective function that was just defined. Further, it's very sensitive to outliers, which I'll discuss a little bit more when I get to the way that we've sort of set up our objective function. So instead of sort of thinking about starting from this heuristic algorithm world, the way that we're going to approach clustering is to use a semi-definite programming relaxation of the clustering problem. So a semi-definite programming relaxations are a general tool that you can use to get a convex relaxation of an NP-hard problem. So something that we can actually solve efficiently, but it's a relaxation of our original problem. And in particular, the semi-definite program I'm going to use is called the max k-cut problem, max k-cut semi-definite program. And the reason that these are so useful to have this convex relaxation is that this is a very powerful relaxation, and that it maintains a lot of the information from our original problem. So the solution that we get out maintains a lot of information about which points we want to put into the same cluster, even though it's not going to actually correspond to an exact clustering in most cases. So the key when you do any sort of relaxation of an optimization problem is to say, okay, relax the problem so I could solve it, but now I have to go back to my original space. So I actually have to map back to a clustering rather than a relaxation of a clustering. So rounding the solution is key in order to actually make use of the power of semidefinite programs. And so I mentioned that we had these two different companion papers, one focused on this iterative linear optimization map. And that's going to sort of be the key of how we think about rounding this semidefinite program, is that we're going to use this new optimization tool to solve a sequence of semidefinite programs in order to actually round our solution. So we're going to iterate on our solution and actually define a sequential clustering problem. And the nice thing is that we have nice experiments and we have nice visualizations of the results that we get, and they match our intuition about this being a way that will preserve much more information than sort of the traditional way of rounding these semidefinite programs. So semidefinite programming, I've mentioned it a couple times now. And what exactly is that? It's a type of optimization problem. So semidefinite program is an optimization problem where the variable is a semidefinite matrix. So a semidefinite matrix means that it has eigenvalues greater than or equal to 0, and it's symmetric. And we have a linear constraints and linear objective function. So that is what defines a semidefinite program, is if your variables fall into this matrix structure, that it's semidefinite program, and you can write your constraints and objective function in a linear way. The nice thing about semidefinite programs, we can solve them efficiently. We can solve them in polynomial time. And they're most often used as convex relaxations to combinatorial optimization problems that are NP hard. That's sort of where semidefinite program gets a lot of the buzz, and more recently, sort of sum of squares has been an area in computer science that has been making use of these semidefinite programs to solve hard combinatorial optimization problems. But once we solve this, we actually need to sort of map back to that combinatorial space, and that's where randomized rounding is often used. I mentioned that they're used on these NP-hard problems, and I said that they're very powerful. And by powerful, what I mean is that we often get approximation guarantees. So by this, what I mean is that we can actually bound our solution versus the optimal solution and how close we are, rather than relying on a heuristic like one of the k-means variance of algorithms where we don't get any guarantee on what that solution looks like. Here, we actually can bound in comparison to the optimal. And that's one of the reasons why people really like these semi-definite programming relaxations. So my PhD advisor, David Williamson, and his advisor, Michelle Goins, sort of came up with this idea of using semi-definite programming relaxations in the context of one combinatorial optimization problem called the max cut problem. So this was in the 90s. It sort of renewed a lot of interest in this kind of optimization. So for the maximum cut problem, we have a graph, and we have weighted edges between the nodes of the graph. And the idea is that we want to split the nodes into two sets so that we maximize the weight between those two sets. So if I look at the pink and the blue, and I put a weight of 1 on all of these edges that I've drawn here, then I would get a weight of 5 edges being across the cut. So those are the 5 edges that I've cut by putting the vertices into these two sets. And when coming up with this idea of using a semi-definite program for this problem, then they were able to show that they got a really high approximation guarantee on the solution, and it's actually the best possible under the unique games conjecture. So under the unique games conjecture, this is the best possible algorithm you could guarantee unless p equals np. So it's a pretty strong algorithm from our standpoint. And it does already look a little bit like a clustering algorithm, except for we're sort of limited to having two sets. So we have this like, okay, I'm maximizing weights, so maybe that could relate to distances, but I'm in that setting still of just being able to like separate into two, whereas I want to separate into maybe 3, 4, 5, etc. groups. But we can think about our problem as relating to this problem because we can think about putting weights on between points, which will represent distance between points, for example, and trying to maximize the weight of those weights that are cut by putting points into different groups or different clusters. So in particular, the clustering objective function that we're going to look at is to say, look at all points that are put into different clusters and sum up some non-negative weight of those points. So we've put some weights on the pairs of points, and we want to maximize the weight of ones that are in different clusters. So this is like the max cut, except for now I'm allowed to put them into k groups rather than just 2. This can actually look really similar to the k-means objective function, because I could define this quantity to be mxy, the distance squared. And so that would then say like, since here I'm minimizing the distances within that are in the same cluster, that's the same thing as maximizing the distances that are in different clusters. But the key difference here is that we're not weighting by the size of the cluster. So we are not weighting by the size of each subset. The difference is that the first objective function above our objective function is going to prioritize more balanced clusters. So for example, if you have an outlier point, k-means is very likely going to put it in its own cluster. And that's because of the fact that that will have a very small distance to itself, its mean, or if you have a couple of outliers, they'll be close together. Whereas in our objective function, those points will likely be grouped into whatever cluster is closest to them. So that will be sort of the difference between the two objective functions, but they're very similar in how they behave. So I've defined how I'm going to think about clustering. I'm going to try to maximize these weights of points put into different clusters. And now I have to think about actually solving that problem. And I'm first going to attempt to solve it in a way that I'm not actually able to solve. So I'm going to do that by saying, okay, I want to represent points as being in the same cluster or in different clusters. And how I'm going to do that is I'm going to use a vector representation. So I'm going to have a k-way simplex, and I've put a 4-way simplex down here, where I'm going to have, in this case, it would be 4 vectors that are sort of the farthest apart that they can be. So these are the farthest apart that they, in terms of dot product, where the dot product here of any 2 points, any 2 vectors that are not the same, is going to be equal to -1 over k minus 1. So these are trying to get away from each other. And what I'm going to do is say that that's going to be my representation of whether or not you're in that cluster. So for every one of my data points, I'm going to say you have to pick one of those vectors to be. Your VI, your vector, has to be one of those vectors. So you have to sort of assign yourself, like this one represents cluster 1, and this one represents cluster 2, etc. And you have to pick one of those to be in through this constraint here. Then my objective function of maximizing the weight of points not in the same cluster can just be written in this linear way. where this is just ensuring that because I have this -1 over k minus 1, that I get the proper scaling if they're in the same cluster versus not the same cluster. And if I could solve this problem, that would be great because I would solve my original problem. And I would say, great, if you are equal to A1, you go into cluster 1. And if you're equal to A2, you go into cluster 2, etc. But I can't solve this problem. It's NP hard, just like all the other clustering problems that we've seen. So just like the k-means objective function, this is NP hard. And so what we do is we relax this. And to do that, we allow those vectors, the VIs, to not only take on one of those AI representations, but now they're actually allowed to be unit vectors. So here, my VI is now allowed to be a unit vector, but I put some restriction on how far apart they can be, to sort of try to represent that simplex representation, but in a way that I'll actually be able to solve. So I've relaxed that combinatorial constraint that you have to be one of those AIs, and I've relaxed it by saying that now you're allowed to be any vector. However, you have to maintain this dot product constraint, which is equivalent to putting this into a matrix representation where I have X be my dot products between vectors. So any semi-definite program can be represented as vectors and their dot products. And so this is the same thing where I can clearly see that this falls into the semi-definite programming framework. So this is called the max k-cut semi-definite program, and it has been studied before. It has also been looked at with respect to clustering. But the thing that's nice about this representation is that if you look at sort of the vectors you get out, they're maintaining a lot of the information from the original problem. The downside is that you're getting vectors and you're not getting actual clusterings out of it. And so a way to sort of visualize this is that we've allowed these each data point to be a vector, where the ones that are close together are the ones that we want to be in the same cluster, and the ones that are far apart are the ones that we want to be in different cluster. And so how this problem is has been rounded before is to say, okay, I'll generate k random vectors, unit vectors, and I assign a point to its closest one. So this one would go to map to this one would map to this, and these two would map to here to get out a k cluster. So if this was k equals to 3, I would generate 3 random vectors. With randomized rounding, you can de-randomize this. You can de-randomize this procedure, and but it's just very computationally intensive. It's very restrictive in terms of its polynomial and some coefficient that you really don't want to ever see something be polynomial in. And so if we think about this randomized rounding, one of the problems with doing this is that we're likely to miss a cluster, or we're likely to sort of, because we have these k random vectors, we're likely to sort of be close to two groupings of these vectors. And so we're not necessarily making use of all the information that we're getting out from this vector representation. And so this leads to the idea that, actually to go back to the slide, is that once we got these vectors, I had this notion of like, okay, I want to maintain the information. I want vectors that are close together to go to the same cluster. I want vectors that are far apart to go to different clusters. That in itself is a new clustering problem. I'm thinking about grouping those vectors in a way so that vectors that are far apart are in different clusters. So in essence, I've defined a new clustering problem. And that's exactly sort of the new take on how to think about rounding this, is to say, this generates a new clustering problem. So why don't I solve that new clustering problem using a semi-definite program relaxation again? and I just keep going. So if you think about, I want to keep going until the solution is integer or is actually a clustering. And by integer, what I mean is that I get back to that simplex kind of space. So my xij are either 1, indicating these points are in the same cluster, or it's equal to -1 over k minus 1, and it's in a different cluster. So they exactly align to exactly k vectors. And I could just take out those k vectors and say everything that looks like this vector, you're in cluster 1. Everything that looks like this vector, you're in cluster 2. So this is a representation of what happens when you do that. So this is our matrix X. And the first time that we solve the clustering problem, we've arranged X by the underlying clusters that were used to generate the data. And you can already see sort of a block formation coming out with the yellow. But it's not perfect. You can sort of see that structure, but you also see these sort of greenish points, and it's still a little bit fuzzy about the end, about how it would be rounded. And so if we take that information, those new vector distances to inform a new clustering problem, this is what we get on the second round. And it looks a little bit more like a block structure. So it looks a little bit more like an integer solution, and etc. And in the end, after just 3 iterations, we actually get to an integer solution, meaning that we get to a very clear clustering where we're not doing any rounding. It is exactly telling us the k clusters to output. Oops. And to give another like just visual representation of the difference between these 2 roundings, this is using the same underlying data. One is using the randomized rounding on the left-hand side and the resulting cluster, and it's actually the best out of 50 rounds of running that random process. And then the right-hand side is doing the iterative method, where you then return the end clustering. So you can see that the clusters are much more succinct on the right-hand side, and they're much closer together, the points, and we've actually sort of improved the objective function. And in this case, it looks like a more natural clustering. So now that I've sort of set up why we might want to think about this kind of rounding for the semi-definite program, we have to then think about when I'm actually thinking about these vectors or these matrices be informing the next round, what do these matrices actually look like? And so we're going to first take a look at the underlying feasible solutions, the underlying matrices, and then think about how does this map sort of perform over time, and what can we learn about what can happen when we do this procedure. So the elliptope is defined as the set of semi-definite matrices where the diagonal is all ones. And the elliptope has actually been studied quite a bit to sort of understand its structure. And then the K-way elliptope is the elliptope, but now we're putting that constraint on the off diagonal. So this is the set of matrices that are actually feasible for our original semi-definite program. So what you can think about is happening is that we take the elliptope, and then the K-way elliptope is intersecting it with an orthant, where that orthant is cutting off more and more and more of the possible solutions as K increases, because you have a stricter and stricter constraint on those Xijs. This is a picture of, oops, didn't mean to zoom in. This is a picture of the elliptope when you have n equal to 3. So you only have 3 data points. I won't go into all the colorings of the points yet, but I just want to point out these red points here. These are what we call the vertices of the feasible solution. So these particular points. And if you think about what it sort of looks like, it looks like you've taken like a pyramid, and then you've blown it up a little bit, so it got like puffy on the sides. And so it doesn't look like you sort of inflated a little bit all these like previous faces. But it's actually a very hard thing to understand as you increase beyond n equals 3. There's lots of sort of surprising behavior of what this feasible region looks like as you increase n. So the vertices of the K-way elliptope, I talked about like the vertices here. We have these 4 vertices. In general, a vertex of the elliptope is defined to be an extreme point with a full dimensional normal cone. And I'm going to break that down a little bit for you. The normal cone is to say, if I looked at all the matrices that you could give me such that I look like the best point, that's the normal cone. So if we think about if our feasible region had some point here, and I took an objective function that was sort of pointing upwards, it would look like the best point, but it would also look like the best point in several directions. So I'd get sort of this cone of what looks like the, if my objective function was pointing in any of these directions, I look like the best point. And an example of something that might not have a full dimensional normal cone is something where only if am I pointing exactly tangent to this point, do I look like the best point for this feasible region. But if I wiggle it at all, so if I start pointing like this, all of a sudden I'm gonna actually say like, actually this point looks like the best point. So you won't actually, you are very sensitive, and as soon as you sort of move, if you think about changing the objective function just a little bit, you're gonna go to a different point. So a full dimensional normal cone, I mean, it's nice to think about it as just like you're at a pointy point. You're a pointy point of the space. And in particular, how pointed you are is that your normal cone is full dimensional. And the nice thing that we realize about the vertices is that the vertices of the K-way elliptope are exactly the clusterings. So they're exactly those integer solutions. So they're the solutions that look like or minus, oh, sorry. Let's put these 2 points in the same cluster and this point in its own cluster. The points that have the 1 and -1 over k minus 1 structure. And so the vertices, or the pointy points, the points that we sort of hope to end up at, are exactly corresponding to those integer solutions we want to round to. Those integer solutions that we understand we don't even have to round you in the end because we understand exactly what the clusters you're telling us are. So for the way to sort of understand why this is the case is that if you're at one of these clustered matrices, if you take any matrix that has the same sign pattern, you are actually the best solution for that for that M matrix. So that sort of tells about why it's full dimensional, is because I can change in any of those directions, any of those xij's, as long as I maintain the same sign pattern, and I will still remain the optimal solution. And the reason that is the case is that when we have something that's positive, I'm putting a 1 there. And when I have something that's negative, I'm putting a -1 over k minus 1. So I'm sort of exactly putting the weight where I want to put the weight. And then in the other direction, suppose that you don't look like one of these clustering matrices. So you have something that's not -1 over k minus 1 or 1 in value, then we can actually show that that's a direction where the normal cone is orthogonal. So we could actually think about making an improvement in that direction, that you wouldn't be able to be the optimal solution. The reason that I sort of bring up these vertex points is that vertices have a lot of structure. By having a full dimensional normal cone, not only are if you get to that point, we're going to sort of know the end solution, but also that you're going to have a lot of points that then sort of map to that point, to that vertex. Vertices are points on the elliptope that we have a lot of understanding of. So thinking about our iterative linear optimization, to actually define when I said I'm going to use those distances between vectors to inform my next optimization problem. Well, what I'm going to do is that I'm going to put, if I get out matrix X, I'm going to take matrix X, I'm going to add some scaling matrix A, where it's equal to 1 minus k over 2k for all entries. And I'm going to use that as my m in the next iteration. So now I'm thinking about putting in m, and I then optimize again to take a new matrix Y to find that optimizes this. So in terms of why do we have this A here, there's two reasons you can think about having this scaling. One is because we're in that situation where one is saying that you're the same vector, but you're only allowed to go to -1 over k minus 1 to be sort of in different clusters. This is sort of recentering so that those are weighted more evenly so that you have a better balance. The other way that you could think about it is that actually solving this map is thinking about trying to find the closest vertex to your point X. So this is supposed to be the puffy version, and you maybe landed here, and what you would ideally want to say is that this is the closest vertex, so this is the closest clustering that I look like. And just sort of going back to the original motivation, this is the same thing as saying I'm solving that secondary clustering problem where I've just sort of put new weights based on those distances between vectors. So that sort of motivates the reason why we want to think about this particular iterative map in two perspectives. One, it's sort of saying like I got this underlying clustering problem. It led to a new clustering problem. I'm just going to continue to solve it. And two, my vertices are my clustering, so I'm sort of mapping to my closest vertex. I'm mapping to my closest point, where I have to sort of then relax that back to the semi-definite program. So with this map, I run it repeatedly, and I've told you like I want to end up at a clustering, and that is the ideal case, right? That's what we sort of want to understand about this map. Where do we end up? So ideally, we want to converge to a vertex because that's a clustering. Even more ideally, I'd like to converge to the closest vertex, but that's actually not always the case. Because we have this convex relaxation, we're not always going to end up at the closest vertex, although we do see that we oftentimes do. But we will end up at a clustering, hopefully. And so to think about the points that we can end up at, we have to think about what are sort of the fixed points. So when I think about this linear optimization, iterative linear optimization problem, I then can think about when do I stop? It's when I'm at a fixed point, meaning that I no longer, if I look to optimize based on my new distances, I actually just end up where I was. So I just don't move. So a fixed point is a point such that you look optimal to yourself. And an attractive fixed point is an even better fixed point because it says that if you're in a ball around this, you're at most distance epsilon from this point, then you're actually going to converge to there. So thinking back to like the vertices, if we're sort of in this region here, we sort of expect to converge to that clustering. So we want to understand what are the attractive fixed points. The other paper that talks more about this iterative map as a general tool for optimization, we can actually use the results from that to show that this map A converges. But we don't have any result on the rate of convergence. So we have our experiments that show that it's actually very quick to converge, but we don't have any result actually on the rate of convergence. But at least we are going to converge to a solution. And the second thing that we get out from new results in this particular paper is that the vertices are the attractive fixed points. So these are the points where actually you are guaranteed once you're within that ball around that vertex, you go to that point. And there are no other points that have that characteristic. So the clusterings are the attractive fixed points. And this comes out of that same idea of thinking about the sign pattern, because that gives this distance. So as long as you have the same sign pattern, you will map to that vertex. However, the downside is that these are not the only fixed points. There are other fixed points, but they're not attractive. So they're not attractive in that there are directions where you are not going to map or you're not going to converge to that point, but they can still be attractive from certain directions. So from a limited amount of directions. And we don't have a clear understanding of in what cases you would actually go to these. So for k equals 2, if we're back into just that elliptope case, just the max cut problem, then we do have a characterization of these fixed points, and these are the blue and green points that are put on the elliptope here. So we actually know that you're a fixed point if and only if you have this sort of funny structure where your matrix squared is equal to a diagonal matrix times yourself. So that gives like a lot of structure to what these points can look like. And another characterization that's equivalent is to say that you have a set of orthonormal vectors such that you are this even weighted sum of those vectors transpose times themselves. So you actually have like an exact characterization of what these points can look like, but only in the case of k equals 2, we don't have a characterization for larger k. So these are the points here. And what you can think about is that why do these other fixed points come about? And it's a little bit because they look like points where you're like tied. So if you think about like these green points, you're sort of, if I just sort of wiggle a little bit to the left, wiggle a little bit to the right, I'll actually end up going to a vertex. I'll go to a clear clustering. But when I'm at that point, I'm like torn between those two clusterings. I'm exactly sort of tied in information. So you can think about this as like when two vectors are equidistant apart. And so I'm a little bit uncertain about like which way do I go. And the same thing for the blue points. This is actually when like all the vectors are a little bit uncertain about what to do. So they're all sort of like, I don't really know exactly which direction to go in. And I have these tied distances. So to conclude with some experiments, we generated some data using a mixture of Gaussians with just in the hundreds of points. These take 2 to 3 minutes to solve in Python. Using SCS solver for the semidefinite program. You could see improvements in the computation time by implementing like an ADMM algorithm, for example, but we just use this like built-in solver. And then for the underlying data sets, we generated 10 different data sets and solved for different values of k. So not only the k that was used to generate the data, but also other values of k. And we found that this iterative map converges in 1 to 3 iterations and always converges to a vertex. So it always actually gets that clustering. And compared to randomized rounding, where we took the best of 50 trials, we saw improvements both in the objective function and the random index, which looks at it in comparison to the like original clustering. So also one of the key takeaways is that the difference that we see in objective function and in random index is greater as k increases. So as you have a larger number of groups, you actually see a bigger payoff of using this new rounding for the semi-definite program versus the randomized rounding. And that makes sense given the randomized procedure. You'd need to take lots and lots more trials to try to get around the fact that it doesn't perform very well when you have large amounts of k. So I think the key thing here to sort of think about is that semi-definite programming relaxations are really nice convex relaxations that preserve a lot of information. And this is a new way to think about rounding in the context of clustering. I think it could be really interesting to then think about this kind of rounding for other semi-definite programming relaxations. So looking at any of those sort of sum of square um, relaxations that have been used. And then in this particular context for clustering, things that we don't know that we would still like to know would be convergence rate and an exact characterization of the fixed points and detection of improving directions. So just in case we ended up at a fixed point that was not a clustering, is there a way we could then sort of wiggle ourselves out of that situation so that we could get to a clustering? And that is everything. So thank you. Oh, let me go back.
Alice, thanks a lot. We have some time for questions. I'll go to the floor first. I had a couple of questions that I jotted down, but I'll hold those for a minute. Not seeing anybody jumping in here. So these are going to be like amateur questions because this is a field that I'm just like on a steep learning curve as you're giving your presentation. But one sort of fundamental question is, the things you're clustering, do they have to be measured on a continuous scale? I mean, you gave examples of mixtures of Gaussians, but
They do not. That's actually one of the nice things about using this objective function is that it's very flexible with how you define those weights. So as opposed to k-means where it is like relying on the fact that you're using like a Euclidean distance, so which it can be used for categorical, but doesn't have as nice of an interpretation. These can be defined however you want. So if you want to think about like the number of categories that you match on as being a distance, or like number that you don't match on being a distance, then that could be the m's that you put into that matrix. And so it doesn't rely on any assumption of how you've defined distances between points.
right. Okay. So you just, whatever distance metric you want to use, you just kind of put it in there.
Yeah.
I see. Yeah, because I think, so one, well, what are the applications of, do you think, does this have like mostly application for like, if we're going to take this into the field, like image, like sort of segmentation of images or detection, like, you know, some of the applications I'm familiar with are like, you know, looking at tumor characteristics from radiographic images, or the other sort of application I was thinking of this kind of technology is like on the other end of the measurement spectrum is like people do a lot of in natural language processing or that sort of thing. People do a lot of clustering of text, you know, to find like patterns and things like that. So the first
So one of
example I think of is like a high resolution thing measured on almost a continuous scale, like X, Y. Whereas the other is sort of like, I don't even know how to set up distance metrics. But anyway, what's the, I'm just trying to get a sense of like the,
Yeah, so one
when
of
you
the
bring this out to the field, what kind of problems?
So if you like were to run k-means, for example, and you're finding that it's like taking like you're finding your clusters are very imbalanced, which actually like, so I just had a project where students had to submit something on clustering. This actually occurred in a lot of the results, is that you'd see like these little small clusters get sort of taken away from the main cluster, which still has like 90% of the data. And
Yeah,
that comes from the k-means objective function and how it sort of has to define um, where it's sort of balanced by it has that weighting by the size of the cluster. So that's actually a case where I was thinking if you wanted to sort of make it so that it had to find more balanced clusters, I don't just want to find these sort of like special cases. I want to actually find underlying group structure of the whole data set. That's something where like this kind of objective function could do, which could probably improve the result.
right. Okay, that makes a lot of sense. And these are, is it like k-means instead we wind up with hard classification as opposed to soft classification?
Yes, it is hard classification, yeah.
Okay.
Although with like, so one thing you can think about is the fact that when you just get out those vectors before you do the rounding, they are sort of softly classified because they are not exactly pointing in the opposite, like they're not exactly looking like a K perfect vectors separated. They do have some like wiggle and, and error. So the initial convex relaxation is allowing it to sort of be a soft clustering. And then what we're doing is sort of rounding it to be a hard clustering.
Yep. And so is this, again, these are like high level questions. I'm sorry, maybe for not appreciating like all the sort of inner workings here, but if you were thinking about applying this to sort of discover patterns over, you know, a sample of objects, like a sample of images, for example. So I guess you get a hard cluster in each one, but you could, yeah, I guess you could think of that as like, what I'm trying to think of is like how to characterize, how to separate signal from noise. Say if you looked at repeated measures of, and again, I'll oversimplify, but like a normal brain, you know. Um, so we see like maybe activity, whatever a normal brain is, or sort of under an image under normal conditions.
Mhm.
Um, if I just apply this repeatedly, I guess I could get a distribution of these clusters and then begin to study them that way.
Yeah, there could, I mean, I haven't thought about that like that far, but there is a way you could think about the initial like like the initial matrix as giving you some notion of how certain you are. Like in terms of when I said it, like you're sort of mapping to that closest vertex, you end up traveling some, right? You weren't exactly a clustering, so you end up traveling. And so there is that notion of like, if it just took one iteration, you were likely very close to a clustering. And so it's likely that you weren't in that situation where you have sort of like um, a lot of overlap or uncertainty.
Mm,
And then as you have like more and more iterations, you're more likely to be in that case of like it's pretty fuzzy. And also you likely traveled a large distance to sort of do that rounding.
I see. I see. Yeah, that makes sense too. Okay, that's helpful to sort of like round out a bigger picture. So thanks a lot for those answers. Are there others that have questions? Okay, so it could be a function of 5 in the afternoon kind of
Yeah.
phenomenon. It could be a tail end of the pandemic phenomenon here, but I think
And
I just
also
want to
Joe,
say thanks
just
very much.
yeah, just to your point though, Joe, by the way, like this combines like a lot of different areas of of research. And so there are aspects of it that definitely were new for me to learn sort of to get to this result, which I think so I appreciate your questions of thinking about it from this data science
Well,
perspective.
I mean, I think it's kind of cool that like, you know, the idea of k-means clustering is like really super intuitive and stuff like that, but it also like runs into limitations very quickly. So it's I don't know. I think of this as like getting past some of those is a key contribution here. And again, being a statistician, I'm sort of interested in like, okay, if I have like data, how do I come up with a distribution of these clusters so I can understand their sampling behavior and things like that.
Yeah, yeah.
That's for another day. So, but anyway, yeah. So thanks very much, Alice, for taking the time. And so we'll close it out here. And I suspect I was going to say maybe something about when the next one of these is, but I think they're online. I don't have that at my fingertips. So please check the DSI website for further Wednesday afternoon seminars. And thanks everyone for coming.
Thanks, Joe.